let us start by reviewing a few familiar formulas. So, of course, a plus b to the power of 0 would be 1 whenever it is defined, because if a plus b is non-zero, then it's going to be 1. Basically, for every real non-zero number, for every real non-zero number, it's going to be 1, and 0 to the power of 0 is undefined. So, suppose that this is defined, then whenever it is defined, we're supposed to have 1. And we have another familial formula, nothing surprising here. It's written in a bit weird way to show some pattern. So a plus b to the power of 1 is just a plus b. And here I added, intentionally emphasized the multiplication by 1. And we also have this familiar formula, a plus b squared is 1 times a squared, twice ab, and b squared. And again, we see this 1 appearing here. And maybe you have already noticed this pattern of this triangle of 1s. And if we continue one step further, this formula is also typically familiar from high schools. Then we have that a plus b to the power of 3 is given by this formula. And so there is a pattern emerging here that we can maybe guess or observe. And so we see that a plus b to the power of 3, or some power, is going to be the sum of those products a to some power times b, such that the sum of powers here is 3 in this case, or n for the general case. So the pattern that we notice, that the expression of a plus b to the power of n is sum of terms of this form, where the sum of their powers is n. Okay, so because, that's what we see, that k plus n minus k is n. And we have some coefficients. And what can we say about those coefficients for now? Let's call them c and k. C and k is the coefficient of this expression. Okay, and so then our conjecture is a plus b to the power of n is of this form. It's sum of those expressions with some coefficients, and the binomial formula actually tells us how to compute those coefficients. Okay, and one more thing that we may notice here is the symmetry. Well, we don't have much to observe here in this triangle, but we see that this one is corresponding to this one, and this 3 corresponds to this 3. So this kind of symmetry, and we can actually prove it, because assuming the conjecture that it is of this form, then what we have, if we write b plus a, which is the same as a plus b to the power of n, and open it with the same formula, then we have this expression. But it's exactly the same expression. We're supposed to have a complete equality here, because this is a polynomial in 2 variables. And since those polynomials are equal, their coefficients are supposed to be equal of all the corresponding terms. So the coefficient here in this sum, the term a to the power of k, beta to the power of n minus k will also appear. But its coefficient is going to be c. And here, the coefficient, we need to replace k by n minus k. And so, in order for these to be equal for all AB, we must have this symmetry that we have observed. Of course, we are going to prove it all. And another thing that we notice is actually this triangle pattern. So, this triangle of ones, so we see the ones over here. This, we can write this conjecture that starts with ones as saying that c and 0, the first coefficient and the last coefficient, are 1. Okay, and so if we arrange those coefficients, this is up to the 3rd power. So we see this envelope of 1s, and so our conjecture is that we have seen this pattern appearing here. And one interesting thing that we can notice in this pattern, that this 3 is the sum of 1 and 2, and this 3 is the sum of these 2 and this 1, and we have this kind of symmetry here. And the same, if we were to continue this same pattern, this is called the Pascal triangle, then this 4 appears as the sum of those terms here, and the 6 appear as the sum of those, etc. So you get the idea. So we can formalize this as a conjecture for this coefficient c. C now stands for a coefficient, but then again, this c is also conveniently can stand for the name choice, and we will see the justification for this name. And in this expression, it's actually typical to denote this coefficient by the letter c and k, exactly because of the word choice. So we can write now this conjecture that the term c in the n plus first row, for example, this term, is the sum of a term that comes before it in the previous row, and a term that comes right after him in the previous row. So, for example, if we apply to this 10 over here, then this 10 is the sum of this previous term and then the one after him. So this is the conjecture that we will also prove. But we have noticed a pattern, and now we'll try to prove it. So now we need some prerequisites from combinatorics in order to prove it. And so suppose we're given the following question. We're given n people and n seats, and the seats are numbered, and the seats are arranged along a straight line. There's actually a difference if they're arranged in a circle, but we'll not go into it. So suppose the seats are numbered, and then we ask people to sit on the seats, and then we take a photograph. And so the question is, how many distinct photographs can we take when the peoples are seated on the seats? Each person can sit only on one seat, and so the order here matters. Like, it matters which person sits on the first chair and which person sits on the fifth chair, etc. So how many possible photographs can we take? Well, let's count. So for the first person, we have n possibilities, right? He can choose any of the n seats. And the second person has n minus 1 seats, and the one after him has n minus 2, etc. And then the last person will have only one available seat. And so the number of combinations is denoted by n factorial. It's called n factorial. It's a definition that we make, which is convenient for this case. And basically, this is the product of all the numbers from 1 up to n. This is another way to denote this product. And this is the number of possibilities. Okay. So now let us ask, and again, we define 0 factorial to be 1. Now, this may seem weird for now, but there's actually good justification for this. It's very convenient to define this, and there are good reasons to define it this way. But what justification can we give intuitively? Well, it's not such a good maybe justification for now. We'll give better ones later on. But there is only one way, the trivial way to arrange 0 elements on a line. Sounds kind of bad, but we will improve it. So for now, let's take this as definition, that 0 factorial is 1. Okay. So let us now ask another question. Suppose that we have a class of n students, and we ask the question, in how many ways can we choose a delegation of size k of these students? So suppose we have a class and with n students, and we want to choose the football team. Okay. And so how many possible combinations of football teams could we have? How many choices? Okay, and so we can start applying the same reasoning again. So for the first team member that we choose, we have n possibilities, but let's write this as n minus 0. It might look weird to write this in this way, but it makes things easier. You'll see in a moment why. And so for the second person, we have n minus 1 choices, and for the case, here's the reason for this n minus 0. For the case person, because the first choice we have already made here, we have n minus k minus 1, because note that this is exactly k choices because of this k minus 1 here, because starting from 0 up to k minus 1, there are exactly k numbers. So for the first, we have n or n minus 0, and then for the second, n minus 1, and for the case, we have n minus k minus 1. This is important. So this is the number of choices. And so if we continue this reasoning, so for now we have this product, but there is a subtlety here. Because if we're interested, it's actually two types of questions. If we're interested only in those people, like what is the team, like who are the people in the team, then it doesn't matter in which order we chose them. It doesn't matter if I chose, for example, John to be the first and then Sam to be the second. It doesn't matter in which order I chose them, right? It only matters who's on the team. It only matters now who's the players. And then, since the order doesn't matter, we need to divide by the number of possible permutations in possible orders in which I choose them. Another situation where it matters is that suppose that when I choose this team, then I choose the captain first, right? So the first is the captain, and maybe he gets some I don't know, some amount. and then the second person I choose gets less money, and then the last one get the least amount. In this case, it matters. Those are different combinations because the order matters here. So in case, I hope I made this clear, or suppose that I'm choosing a team and then they're going to compete, and then they're going to be ranked based on their performance in the competition. So in this case, there are more outcomes because it matters the order in which they were ranked in the competition. So when the order matters, this is the result. It is this product when the order matters. When the order does not matter, we need to divide by k factorials because the order in which I chose them doesn't matter. So, and this is denoted by n choose k. This is the binomial coefficient, and we'll see why. So it is this product divided by the possible number of possible internal choices. This is the number of permutation. It divides by the order in which I chose them, because the order doesn't matter here. Okay, and so okay, here's another thing that I wanted to say. Actually, this is actually important. Those kind of considerations are pretty important in statistical mechanics. When you have gas molecules, there was some computation, and that treated the gas molecules as distinct particles. And actually, there was a factor of n factorial, of the number of particles factorial in there, that didn't agree with the experiments. And I think it was idea due to Gibbs that those molecules should be treated as indistinguishable particles. And then this factor, he factored out by n factorial, and then the results matched the experiments. So it shows just that those considerations are very important. So let us go on. So now let us do this trick to write it in a more neat way. So what I'm doing here is that we have this n times n minus 1 times n minus k, and then the next element here, suppose that I want to continue and make it go down all the way up to 1. So I need to subtract n minus k, and then to subtract n minus k plus 1, etc., till I get to 1. And so this, by definition, this number is n minus k factorial. So that I wanted to add this here, so that I will have, as you guessed here on top, I will have n factorial. But in order for this to be correct, I need to correct this. So I divide by this in the denominator. And so now we see that this expression, the binomial coefficient, or also referred as n choose k, is therefore equal to n factorial divided by k factorial times n minus k factorial. Okay, and so this expression gives the answer to the question, in how many possible ways can I choose k elements out of n elements where the order doesn't matter, right? So this is the answer. And so now we see another reason why it's convenient to define 0 factorial as 1, is that we want this expression to be defined, because there's only one way to choose 0 elements, is just not to choose anyone. But maybe even a better justification, there's supposed to be only one way to choose n elements out of n elements, which means that I must choose them all, right? And so when I plug in n here instead of k, then I'm going to have n factorial here divided by n factorial, and here n minus n, which is 0. So in order for this to have the meaning that I want to assign to it for all the numbers from 0 to n, it's better be defined that 0 factorial is 1. So this is another way to see the justification for this definition. Okay. So we set that. So we really want to mean this, to have this combinatorial meaning as the number of possibilities to choose k elements out of n elements. And so in what follows, we will prove that this cnk, which is also denotes this coefficient, is exactly this. Those coefficients that we saw in our conjecture so far are exactly the number of ways to choose k elements out of n elements, and we'll see how it is related. Okay. So now this binomial coefficient that we have introduced has a few properties. So this property is something that we've already seen. It just follows from the fact that we define 0 factorial to be 1, right? Okay, and the symmetry we kind of conjectured it, but let's prove it directly. And this conjecture that we have will also prove it. So the first property, as I mentioned, it follows from the definition that 0 factorial is 1. Okay, and how about this one? Okay, so let's prove it by computation, right? Let's prove it by direct computation. So we have n choose n minus k. So we have n over n minus k, and here n minus k factorial. This is just the definition, but then n minus k is just k factorial, and so it is this expression. So we see this nice symmetry. But suppose that we want, to see if we can prove it based on the definition and the combinatorial meaning of the expression, namely choosing k elements out of n elements. And if we want to give a combinatorial proof, we can give this following story. Suppose that I have n elements and I want to choose k elements. Then actually, to each choice of k elements, there corresponds a choice of n minus k elements, because choosing those first k elements that I choose to include in the set is equivalent to choosing n minus k elements which I choose not to include, right? And so for each choice of k elements, there corresponds a unique choice of n minus k, the complementary choice, right? Because to choose those k elements, I could choose them directly, or I could choose the n minus k elements which I choose to exclude, right? And so this is basically the proof, the verbal proof. It's a combinatorial proof. And so it is nice to have, for the intuition. So for each choice of k elements, we have a bijective correspondence to a unique choice of n minus k elements, and therefore those must be equal. Okay, so how about this expression? Well, let's prove it algebraically first. Let's just compute it. So plugging in the numbers here, so we have n factorial over k minus 1 factorial, and here n minus k minus 1 factorial, and this is that just by definition. And now we can take the common expression here, so we have n factorial on top here, and here we have k minus 1 factorial, which appears here. And so if you factor it out here, we will have this k over here, and then here the common factor that we have is n minus k factorial, because this is actually n minus k plus 1 factorial, so it's one step ahead. And so when we factor it out, this is what we have inside. And then when we bring it to common denominator, here basically we have n minus k plus 1, and here we have plus k. So on top, you're going to have n plus 1 on top, and then the product of those in the denominator. And so here on top, this is exactly the definition of n plus 1 factorial. And then below, what we have is this. This is exactly n plus 1 choose k, because we divide by k factorial, and then we take n plus 1 and subtract k. But now let us give a combinatorial proof of that. So if we look at the combinatorial proof, suppose that we have a class of n plus 1 students. So their names will be A1, modern space name, sci-fi names. Their names will be A1 up to En, and one special student whose name is going to be Johnny, right? And so now let us give a combinatorial proof that to this expression, that actually the sum of those is n plus 1 over k. So the meaning, choosing k elements out of n plus 1 elements, we know the meaning. So suppose we ask the following question: in how many ways can we choose k classmates out of Johnny's class? Okay, and so on the one hand, we already know the answer. On the one hand, it's just n plus 1 choose k. This is the definition. And on the other hand, I think there's a very nice quote that is attributed to Paul Erdős, who said, whenever we count something in two different ways, we get a theorem. So let us count exactly the same number of choices, the same possibilities, but in a different way. So choosing this team, we could decide that Johnny is not in the team, right? And then we have to choose all the k team members out of the n remaining. So I wrote this in a different order. Suppose that we know that Johnny is in the team. Suppose that we decided that Johnny is in the team, then basically here we don't have a choice, and then we have to choose the k minus 1 remaining team members from the n team members. So we have n choose k minus 1 possibilities if we know that Johnny is on the team. On the other hand, if Johnny is not on the team, right, then we need to choose the k team members out of the remaining out of those remaining n elements, right? And therefore, since we counted the same thing twice in two different ways, we need to have this equality, And basically, this is valid for k greater or equal than 1. We would want to extend it further, for example, for k equals 0. But at least in this combinatorial setting, we need k to be at least 1, because we know that Johnny must be in the class in this way that we have proved. So the class consists at least of one classmate. Sure. And therefore, what we have is we have this binomial expression expansion theorem. So now let us prove it. Well, I think we now have all the tools to prove this theorem. So what I claim is that something that we've led through this lecture is that a plus b to the power of n is this sum, right? And so how were we to prove it? So what we need to prove here is that we take a plus b to the power of n, and basically we need to open all those brackets all at once, right? And so when we open a bracket, so basically we multiply every a here with every a and b here, right? And so eventually, when we open all the brackets massively, an expression that we obtain here is that we need to choose a from some of the brackets, suppose out of k of them, and then the rest are b's. But how many choices do we have for choosing a? So we have n brackets here, right? And so out of k of them, we're choosing a. So we have n choose k possibilities, right? And then for the rest of them, we have b. And so since the multiplication and addition are commutative, the order of choice in which we chose them doesn't matter. And so in total, we will have n choose k terms of this form. And since we're doing it for every k, then we need to sum over all of them to get this expression. And so, for example, there's only one way to obtain a to the power of n. It's basically choosing a in all of those brackets, right? It's just choose a from here, times a from here, times a from here, a times a from here, times a from here, and this is going to be a to the power of n, and there is only one way to do this. Therefore, there's only one way to choose a's out of all of them, so it's n choose 0, which is 1. And the same for b. We have to choose b from all the brackets, and then there is only one way to obtain b to the power of n. But since we have in total n brackets, if in k of them we choose a, then in the rest we have to choose b, and then we have n choose k such choices. But if you're not satisfied with this kind of proof, let us prove this by induction, right? And so let us prove this by induction, but another remark that I want to say about the coefficient. So now let us define n choose k to be 0. It would be a definition for k greater than n. It's a matter of convenience. And what would be the reason for this definition? Well, there is no way to choose more than n elements out of n elements, and there is no way to choose, for example, k that is negative. There is no way to choose a negative number of elements out of n elements if we still want to extend this meaning of n choose k as the meaning of number of possibilities to choose k elements out of n elements, so we can now extend it to all of integers. But we'll see another justification for that shortly. So now if we, so basically, as I say, if we wish to assign this meaning to this for all integers, then for 0 factorial is defined to be 1, and then we also define this to be 0 for k greater than n or k smaller than 0, and then this has this meaning, but we'll see another convenience here. So now let us prove this same formula by induction. So quoting Paul Erdős here, I think once again, I think he said that something that is very true: behind every deep result in mathematics hides a proof by induction. So basically, when set theory is the axioms are being laid for set theory and being axiomatized, one of the axioms is the axioms of induction, or the axiom of existence of an inductive set. This is very important. And then basically, even such properties of natural numbers that addition is commutative can be proved or needs to be proved by induction. Okay, so without further ado, let us prove this formula by induction. So the first step would be to show that for n equals 0, n equals 1, the formula is correct. So for n equals 0, by definition, those are 1. And for example, for n equals 1, what we have this formula that we have already seen. A plus b to the power of 1 is just a plus b, and we can write those ones here, and then it just follows exactly this pattern. So we can write this as the sum. So for this case, we're covered. At least for n equals 1, the formula is correct. And so now we suppose that the formula by induction, that for n, this formula is valid. And what we need to do, we need to prove it for n plus 1 for the next step. This is the inductive step. So now what we do is we like to compute a plus b to the power of n plus 1. And so it equals to a plus b times a plus b to the power of n. And now instead of a plus b to the power of n, we plug the induction hypothesis over here. And so now if we were to open the brackets, we were to multiply this sum by a. So we have here a to the power of k plus 1 times b to the power of n minus k. And what we have here is that when we multiply this by b, we have n choose k, and here a to the power of k, b to the power of n plus 1 minus k. So it's nice to have this power of n plus 1 here. And now we'll use those definitions that we introduced previously to write this in a more neat way. So now what we're going to do is a very important trick for shifting indices. So basically what we have here is this k runs from 0 to n, and we're going to rename, introduce a shifted index. Well, let's call by L. L would be k plus 1 here. And so instead of k plus 1 here, we are going to write L. And instead of k, we're going to write L minus 1. So it's written here. And as k runs from 0 to n, L ranges from 1 to n plus 1. Okay, so here it works. But and so when we plug it in here, so it's n minus L minus 1. And then when we plug it in here, so when we open the brackets, we see that it is n plus 1, which is good for us because the sum of the powers here is now n plus 1, which follows the pattern. And now with these definitions, we have defined this coefficient to be 0 for L, for expression here that is negative. We can write that this is the same sum and extend for L to run from 0 up to n plus 1, which is what we wanted. Right, so using this definition, it is convenient. We will see a better justification. But for now, let's use this definition that this has been defined as 0. So we can now extend the sum, and actually this sum can be rewritten as sum over L, as L goes from 0 to n plus 1, and this coefficient over here, and this power is n plus 1. Okay, so now we need to take care of the second sum, right? And so we're also going to rename the summation, the dummy variable, the summation index L. Both k and L are dummy variables in the sense that they're not real variables, but they're there to indicate summation. They're being summed over. Okay, so let us go to the second term here. So in this second term, what we have is this sum, where we sum k runs from 0 to n, and let's just rename here the variable k to L just for convenience. And so this is, if we plug in L here, then this is what we get. And basically, by the same argument, we can extend this sum to let L run not from 0 to n, but from 0 to n plus 1, because the last coefficient here, n choose n plus 1, is going to be 0 anyway. And so we can extend this. And now that we have done those tricks, we can add those two sums together as we were supposed to do. So finally, we conclude that when we take a plus b to the power of n plus 1, we had that this is the sum of those two expressions, and then they can be rewritten as we've shown. This sum can be rewritten as this sum, and this sum can be is equal to this sum and can be written as the following sum. And then when we add them up together, we have that the coefficient is the sum of those coefficients, right? And this is a to the power of L, b to the power of n plus 1 minus L. So the sum of the powers is n plus 1. And then by the property that we have already proved for the binomial coefficient, right? We already proved this identity, that this is exactly n plus 1 choose L. We gave two proofs by a direct computational proof and a combinatorial proof. So this definition becomes handy once again here, because it enables us to define it in such a way. And in addition, what we have here, that this definition also allows us to define n plus 1 choose. This means when we define it this way, that it applies this formula can be adapted to the case So for example, if I want to extend this formula, n plus 1 choose 0 is the same as n choose 0. And when I plug 0 here, if I define this to be 0 for n choose minus 1, then this formula continue to work even for L choose 0, because this has this meaning. So hopefully this is a better justification. And again, when I plug in here L to be n plus 1, then here we have n plus 1 choose n equals n choose n. And here plus n choose n plus 1. So again, it gives us that justification for the definition that if we want this formula to keep working, then the meaning this should be equal to 0. So n choose n plus 1 should be equal to 0. So n choose m for m greater than n should be 0. All right. And so finally, when we plug this identity into the sum, then this is what we get. And this is exactly what we were supposed to prove, that this is the binomial coefficient of n plus 1, and the sum of powers here is n, and therefore the formula is proved.